Hi, linear algebra students. So we are in the last example of properties of determinants. We're going to finish the example that we started in class. Okay, so we have two vectors, a1, a3, and we consider the transformation. Okay, so we do not know yet it's linear. That's basically what we're proving. From R3 to R, which takes X and outputs the determinant A of the matrix formed by A1, X, and A3. So in other words, exactly this matrix, okay? So in class, what we have done is number 1 and 2. So we just evaluated like T of W just to show you how it works. But then afterwards, we set up the proof that this particular transformation is linear. So in class, we proved that T of u plus v is the same as T of u plus T of v for any u and v in R3. And in this video, we're finishing the proof. So we're doing number 3. We're proving that T of c times u is equal c times T of u for any vector u in R3 and any scalar c. Okay? And it works the same way than number 2. In other words, you could certainly do it by yourself, and I would strongly encourage you to do it. Do it by yourself. Try to get the result using the same method as for number 2. And if you're stuck, if it doesn't work, then you have this video to back you up. All right? So very simple. We consider first the vector u, which is made obviously of u1, u2, u3. So consider u, and that's the only thing we know. Remember, we cannot assume that u has particular components. So we only know that it has 3 components, and that's the only thing we need. Okay? So then what we're doing is we're computing T of cu. So T of c times u. Okay? And actually, I'm going to color code here. I'm gonna use, let's say, orange. I think orange is a nice color. So I'm gonna take the vector u to be in orange. So we're and that's it. So this is T of cu. Okay, how is it gonna look like? Okay. Well, we know that multiplying a vector u by a scalar c is just going to multiply all its components. So we know right off the bat that we're going to have this determinant 2, 0, 1, and then 3, 1, 4. Okay? And then we're going to have like CU1, CU2, and CU3. Okay, at this point, those of you who have quick eyes will realize that you can actually prove number 3 by using the properties of the determinants. In other words, like you will transpose this and you will take out C. Okay, because it's like the row operation that scales down by C. So that scale that multiplies by 1 over C is going to multiply the determinant by the same amount. So from there, you will be able to prove it. However, I want you to realize that this proof doesn't work for number 2. And for that reason, I will use the same reasoning as what we did for number 2, is we will cofactor expand along the second column. Okay, so let's actually write that as well. So yeah, all right. I'm gonna take red, or no, I'm gonna take green actually. So remember cofactor expansion. So you have like plus minus, and here you have like plus minus plus, and you're going down the second column. So what it means is that you're gonna have CU1, CU1, there you go, times the determinant of so 0, 1, 1, 4. Then you're going to have CU2. Actually, here, I have to be careful. I forgot my signs. So there's a negative in front of this one, and this one becomes back positive because it's the product of two negatives. So plus CU2 times the determinant of 2, 4, 3, 1. So 2, 3, 1, 4 in other words. And finally, minus CU3. So CU3 times the determinant like 2, 1, 3, 0. There you go. All right. From there, it becomes actually quite simple because you should realize that C will be a common factor. And that's actually the main part of the proof. It's like the main argument is that since C is a common factor, taking it out will give this. So we're going to have like C multiplied by the big bracket. Now I'm going to keep my signs colored because you're going to see what happens next. And I'm going to also keep the color code on U1, U2, U3. So I'm going to have negative U1 times the determinant. And don't bother computing it, and you will see why. Although there's more than one way to do the proof, as I mentioned earlier. So plus U2, then you have like 2, 3, 1, 4. And then finally, minus U3. And then you have the determinant 2, 3, 0, 1. There you are. And let's close the bracket. At that point, now this is the crucial step. The idea is to recognize that this is actually the cofactor expansion of T of U. So in other words, this bracket that we wrote over here turns out to be equal to C times, and now let's write it down. So it's going to be the determinant. Okay. So again, we have like U1 is in the middle. So we know that U1 is accompanied with a negative sign. Okay. And its determinant will be like 0, 1, 1, 4. Okay. And then the cofactor expansion will take care of the like U2 that's over there. And then its determinant is like 2, 3. So that's what goes on the top row. And then finally, we have like the U3 that goes here. And let's just check that the determinant is valid, 2, 3, 0, 1, which is exactly what we have. Okay? And I have just enough space to write it down. So as you can see, it turns out that what we discovered is C times T of U. So in other words, we prove number 3 regardless of U. So that's it. We found out that T of CU is equal to CT of U for any U in R3. And C in R. And this is what we wanted to prove. Do I have just a little bit of space for that QED? Not really. Okay, but in any case, we're done. All right, hopefully this was helpful. Very important argument showing you the structure of determinants. So see you in class or in the next video.